Tonight, we are going to explore something that Albert Einstein refused to believe for the last 30 years of his life. Something he called impossible. Something he called a defect in the theory. Something he called, with barely concealed contempt, spooky action at a distance. And here is the thing. Einstein was one of the greatest scientific minds in history. He upended our understanding of space and time. He showed that gravity is the curvature of space-time. He explained the photoelectric effect and helped found quantum mechanics. When Einstein said something was impossible, the world of physics took notice. He was wrong. The phenomenon he refused to believe in has since been tested in hundreds of experiments with increasing precision and increasingly airtight methodology, and every single time, the result has been the same. The universe really does work the way Einstein insisted it could not. Two particles, separated by any distance, really do respond to each other instantly when one of them is measured. The connection between them is real. It has been measured, it has been confirmed, it is one of the most solidly established phenomena in modern physics, and it is one of the strangest things in the universe. By the time we are done tonight, you are going to understand what quantum entanglement actually is, not the vague, mystical version that gets passed around in popular culture, but the real, precise physics version. You are going to understand why Einstein objected to it so strongly, and why his objection, brilliant as it was, turned out to be wrong. You are going to understand what the experiments actually show and what they imply about the nature of reality itself. And at the end, we are going to sit with a question that entanglement forces us to face. A question that physicists have argued about for nearly a century, and that no one has yet resolved to everyone's satisfaction. Does reality exist when no one is looking at it? Or does the act of measurement bring reality into being? Let us begin. Let us start with something that seems like it should be simple. What does it mean for a particle to have a property? Take a familiar example. You are holding a coin. The coin has two sides, heads and tails. Right now, in your hand, the coin is either heads up or tails up. You know which it is because you can see it. The property, the orientation of the coin, exists independently of whether you are looking at it. If you close your eyes, the coin does not become neither heads nor tails. It remains whatever it was. The property is real, objective, and independent of observation. This is how common sense works. Objects have properties. Those properties exist whether or not anyone is looking at them. The moon is there when you are not looking at it. The chair in the empty room is still a chair. Reality is out there, and we observe it. We do not create it by observing it. This view of the world is so deeply embedded in how we think that it barely feels like a philosophical position. It just feels like obvious, undeniable fact. Quantum mechanics says it is wrong, not wrong in some subtle technical sense that only matters at the subatomic level and has no real consequences for everyday life. Wrong in a way that has been confirmed in the laboratory, in experiments whose results cannot be explained unless you accept that particles genuinely do not have definite properties before they are measured, that the act of measurement does not reveal a pre-existing value, it creates one. This is the claim at the heart of quantum mechanics, and it is the claim that entanglement makes impossible to escape. To understand why, we need to go back to the beginning, to the early days of quantum mechanics, when the theory was new and no one was quite sure what to make of it. By the late 1920s, quantum mechanics had been formulated into a precise mathematical framework, primarily by Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Niels Bohr. The theory worked. It predicted the results of experiments with extraordinary accuracy. The energy levels of atoms, the behavior of electrons, the properties of light and matter. Quantum mechanics got all of it right, in many cases to more decimal places than any previous theory had managed. But what did the theory mean? What was it actually saying about the nature of reality? This was the question that divided physicists then, and, in many ways, still divides them today. The dominant interpretation was developed primarily by Niels Bohr and Werner Heisenberg, and it is called the Copenhagen interpretation. Its core claim is this: a quantum system does not have definite values for its properties until it is measured. Before measurement, a particle exists in a superposition, a combination of multiple possible states simultaneously. When a measurement is made, the superposition collapses. the particle acquires a definite value, but before the measurement, asking what value the particle has is a meaningless question. There is no fact of the matter. Take the spin of an electron. An electron has a property called spin, which can be measured along any axis, and the result is always either up or down. If you have never measured the spin of an electron along a particular axis, the Copenhagen interpretation says the electron does not have a definite spin along that axis. It is in a superposition of up and down. Both possibilities exist simultaneously. The electron is genuinely both until you measure it. When you measure it, one of the possibilities is realized. The superposition collapses. You get a definite answer, up or down, with probabilities determined by the quantum state. Einstein hated this, not because the predictions were wrong, they were clearly right, but because it seemed to say that quantum mechanics was an incomplete description of reality, that there were real facts about particles, facts about what their spin actually was before you measured it, that the theory was not capturing. He believed that underneath the probabilistic description of quantum mechanics, there had to be hidden variables, real definite properties of particles that we just did not have access to. Quantum mechanics, in his view, was like a statistical description of a gas, accurate on average, but not the whole story. The whole story, he believed, would involve those hidden variables, and it would restore determinism and the idea that particles have definite properties whether or not anyone is looking. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published a paper that they believe demonstrated this point. The paper is known by the initials of its authors as the EPR paper, and the thought experiment at its heart became one of the most famous in the history of physics. Here is the EPR argument. Imagine you create two particles in a special way so that they are entangled. Specifically, you create two electrons whose spins are correlated. The total spin of the pair is zero, which means if one electron has spin up, the other must have spin down, and vice versa. You separate the two electrons. You send one to a laboratory on one side of the world, and the other to a laboratory on the other side. Now, someone in the first laboratory measures the spin of their electron. They get, say, spin up. At that instant, quantum mechanics says, the spin of the other electron is determined. It must be spin down, because the total spin is zero. The second electron, no matter how far away, is instantly affected by the measurement of the first. Einstein's argument was this. At the moment of measurement, the two electrons were separated by a large distance. Nothing can travel faster than light. Therefore, the measurement of the first electron cannot have physically caused the determination of the second electron's spin. Therefore, the second electron must have had a definite spin all along. The spin was not created by the measurement. It was already there. And if it was already there, then quantum mechanics, which says no definite spin exists before measurement, is incomplete. There is a hidden variable, a pre-existing spin value, that quantum mechanics does not describe. This argument is clean and logical. It sounds airtight. If you accept the premises that nothing travels faster than light, and that the result of a measurement on the second electron cannot have been physically caused by a distant event at the same instant, then the conclusion seems forced. The properties must have existed all along. Einstein was convinced this showed that quantum mechanics was incomplete. Bohr was convinced that Einstein had made a subtle but fatal error. The debate between them was one of the great intellectual confrontations of the 20th century. And for nearly 30 years, it remained essentially a philosophical debate because no one knew how to design an experiment that could distinguish between Einstein's view and Bohr's. Then, in 1964, a physicist named John Bell changed everything. Bell was an Irish physicist working at CERN, the particle physics laboratory in Geneva. He sat down and thought very carefully about what Einstein's hidden variable idea actually implied. If particles really do have definite properties all along, if there really are hidden variables determining the outcomes of quantum measurements before they happen, then the correlations between measurements on entangled particles must satisfy certain mathematical constraints. Bell derived these constraints in the form of an inequality, now called Bell's inequality. The idea is this: if hidden variables exist, if particles have real, pre-existing properties, then no matter what axis you choose to measure the spins of your two entangled electrons, The correlations between the results must obey Bell's inequality. The correlations are bounded. They cannot be too strong. But quantum mechanics predicts correlations that are stronger than Bell's inequality allows. Quantum mechanics predicts that for certain choices of measurement axes, the correlations between the two electrons will violate Bell's inequality. This was a stunning result. Bell had found a way to experimentally distinguish between the hidden variable picture and the quantum mechanical picture. You do not have to argue philosophy. You do not have to debate what quantum mechanics means. You just measure the correlations. If they satisfy Bell's inequality, Einstein was right and quantum mechanics is incomplete. If they violate Bell's inequality, Einstein was wrong and quantum mechanics is correct. The experiments began in the 1970s. The first convincing tests were done by John Clauser and Stuart Friedman. More refined experiments were conducted by Alain Aspect in Paris in the early 1980s. Experiments that closed many of the potential loopholes in earlier work. And the result, every single time, was the same. Bell's inequality is violated. The correlations are exactly as strong as quantum mechanics predicts. They are stronger than any hidden variable theory can explain. Einstein was wrong. There are no hidden variables. The particles do not have pre-existing definite spins. The measurement does not reveal a property that was already there. Quantum mechanics is not incomplete. The universe really is as strange as Bohr said it was. This is one of the most important experimental results in the history of physics. It rules out the entire class of theories that Einstein had hoped would restore common sense to quantum mechanics. Any theory that says particles have definite pre-existing properties, that the randomness of quantum mechanics reflects our ignorance rather than genuine indeterminacy, is ruled out by the Bell experiments, unless that theory allows for faster-than-light influences between the particles. And here is where entanglement becomes genuinely, deeply strange. The violation of Bell's inequality means one of two things. Either the properties of the particles are not pre-existing, measurement creates them, not reveals them, or there is some kind of faster-than-light connection between the two particles, so that measuring one instantly determines the other. Most physicists choose the first option. They accept the Copenhagen view. Particles in superposition do not have definite properties. Measurement creates definite properties. The correlations between entangled particles are not the result of pre-existing coordination. They are the result of a genuinely shared quantum state that spans both particles, regardless of the distance between them. But the second option has not been fully ruled out. Some physicists, following in Einstein's footsteps, have proposed non-local hidden variable theories. Theories that do allow faster-than-light influences, but in a way that cannot be used to send information. The most developed of these is Bohmian mechanics, or the pilot wave theory, developed by David Bohm in the 1950s. In Bohmian mechanics, particles do have definite positions at all times, guided by a pilot wave that is sensitive to the entire experimental setup instantaneously. The theory reproduces all the predictions of standard quantum mechanics, including the violation of Bell's inequalities, but it does so by being explicitly non-local. The pilot wave connects everything to everything, instantly. Bohmian mechanics is a minority view in physics, but it is mathematically consistent and empirically equivalent to standard quantum mechanics. It demonstrates that hidden variables are not ruled out entirely. Only local hidden variables are ruled out. You can save hidden variables if you are willing to pay the price of non-locality. Most physicists are not willing to pay that price. Non-locality sits very uneasily with relativity, which insists that no influence can propagate faster than light. And here is where something remarkable comes in. Because entanglement seems to involve a faster-than-light connection. When you measure one entangled particle, the other instantly responds. But you cannot use this to send information. And understanding why not is crucial. Here is the key. When you measure the spin of the first electron and get, say, spin up, the second electron is instantly in the spin, down state. But here is what you cannot do. You cannot control what result you get when you measure the first electron. The result is random, with probabilities determined by the quantum state. You cannot force the first electron to come up, spin up. You cannot encode a message in the result of the measurement because the result is not under your control. It is random. The person at the second electron gets a random result when they measure their electron. They do not know whether the first electron has been measured yet. They do not know whether their result is correlated with anything. They see a random sequence of spin-up and spin-down results. They cannot tell from their sequence alone whether anything at all has happened at the other end. Only when the two sets of results are compared, which requires ordinary, slower-than-light communication, do the correlations become visible. The correlations are real. They are stronger than any local theory can explain. But they cannot be used to transmit information because neither party controls their own results. This is a deep and beautiful fact about quantum mechanics. Entanglement is non-local in the sense that the correlations between distant measurements cannot be explained by any local, pre-existing hidden variable. But it is also non-signaling. You cannot use it to communicate faster than light. The non-locality is real, but it is, in some sense, invisible. You can only see it in the statistics, and seeing the statistics requires classical communication. This is not a coincidence or a lucky feature of quantum mechanics. It is a provable theorem. Quantum mechanics is consistent with the no-signaling principle. If it were not, if entanglement could be used to send information faster than light, then it would be inconsistent with relativity in a damaging way. The universe seems to have been designed so that entanglement is as strange as possible while still remaining consistent with the prohibition on superluminal signaling. Now, let us go deeper. Because the question of whether entanglement can be used to send information, as fascinating as it is not the deepest question entanglement raises. The deepest question is this: what does entanglement tell us about the nature of reality? The violation of Bell's inequalities rules out local hidden variables. It says that the correlations between entangled particles cannot be explained by any theory in which the particles have definite properties at all times and in which no influence travels faster than light. Something about the standard picture of reality, the picture in which objects have definite properties and influences travel no faster than light, is wrong. Which part is wrong? This is the question that different interpretations of quantum mechanics answer differently. And the debate between them is not merely philosophical. It touches on the deepest questions about what science is and what kind of understanding it offers. The Copenhagen interpretation, the most widely taught and most pragmatically used interpretation, says, "Do not ask what reality is doing when you are not looking." The question is meaningless. Quantum mechanics gives you a procedure for calculating the probabilities of measurement outcomes. It works with extraordinary precision. Use it. The demand for a description of what is happening in between measurements is a demand for something quantum mechanics deliberately does not provide and may not be able to provide. This is a clean position. It is operationally powerful, and it has guided the development of quantum technology, quantum computing, quantum cryptography, quantum sensors, with enormous success. But it leaves many physicists deeply unsatisfied. Science is supposed to describe reality, not just predict measurement outcomes. A theory that refuses to say what is happening in between measurements feels, to many people, like a theory that has given up on its most fundamental task. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radically different answer. In many worlds, the superposition never collapses. When a measurement is made and the superposition appears to collapse, what actually happens is that the universe splits. Both outcomes occur. In one branch, the electron is spin up. In another branch, the electron is spin down. Both branches are real. Both continue to evolve. The observer in each branch sees a definite result, because they are in only one branch, but both results are real, happening in parallel worlds. In the many-world picture, entanglement has a natural explanation. The two entangled particles are described by a single quantum state. When you measure one of them, the universe splits into branches in which each possible outcome has occurred. In each branch, the outcome of measuring the second particle is determined by the branch you are in. The correlations are maintained across branches. No non-local influence is needed. The apparent non-locality of entanglement is an illusion produced by looking at only one branch when really both branches exist. Many worlds is appealing to many physicists because it preserves the mathematical structure of quantum mechanics without adding anything. No collapse, no hidden variables, just the unitary evolution of the full quantum state of everything. But it has its own problems. The biggest is probability. In a world where all outcomes occur, what does it mean to say that one outcome is more probable than another? If both spin up and spin down happen, in what sense is spin up more likely? The many worlds interpretation has struggled to give a fully satisfying answer to this question, though significant progress has been made in recent decades. The pilot wave interpretation, as we mentioned, saves determinism and realism at the cost of non-locality. In this picture, there is no mystery about what the particle is doing between measurements. It always has a definite position, guided by a pilot wave. The entanglement correlations arise because the pilot wave connects the two particles non-locally. The world is local in the sense that particles have definite properties, but non-local in the sense that the wave governing their behavior spans all of space. And then there are interpretations that question whether our usual concepts of space and time are the right framework for thinking about quantum reality at all. Some theorists have proposed that quantum mechanics is pointing us toward a picture of reality in which space and locality are not fundamental, in which the apparent separateness of distant objects is an artifact of a deeper, non-local structure that does not have space built into it at the fundamental level. This last family of ideas connects to some of the most exciting research in modern theoretical physics. The discovery of the ADS/CFT correspondence, a profound mathematical duality between a theory with gravity in a volume of space and a quantum field theory on the boundary of that space, has suggested that space-time itself may be emergent, that it arises from the entanglement structure of a deeper quantum system, that the geometry of space, the separateness of distant points, is a consequence of entanglement, not a precondition for it. This idea is still being developed, but it suggests that entanglement is not just a strange feature of quantum mechanics. It may be a fundamental ingredient in the construction of space itself. The connections between entangled particles may be the threads from which the fabric of space-time is woven. If this is right, then the question of what entanglement tells us about reality has a remarkable answer. It tells us that reality is not built from separate local objects that occasionally interact. It is built from connections, from correlations, from relationships that span what we call space. The separateness we experience is real, but not fundamental. At the deepest level, everything is entangled with everything else, and the world is a single, vast quantum state in which the appearance of locality and separateness is a feature of the emergent space-time, not a feature of the underlying reality. This is a breathtaking vision, and it is increasingly not just speculation. It is being worked out in precise mathematical detail by some of the best theoretical physicists in the world. But let us come back to Earth for a moment, because I want to make sure you feel the strangeness of entanglement in a concrete, visceral way before we lose it in the abstraction of interpretations and space-time. Here is a real experiment. You create two photons in a process called spontaneous parametric down conversion. A crystal absorbs a high-energy photon and emits two lower-energy photons that are entangled in their polarization. You send one photon to a detector on one side of the lab. You send the other photon to a detector on the other side, perhaps hundreds of meters away, perhaps kilometers away. You set up the detectors so that they measure the polarization of each photon along an axis of your choosing. You can set each detector to any angle. You run the experiment many times, getting a sequence of results from each detector. When you compare the sequences, you find correlations. If both detectors are set to the same angle, the results are perfectly correlated. Every time, not sometimes, every time. If the first photon is measured as polarized horizontally, the second photon is always measured as polarized horizontally too, assuming the detectors are aligned. If you rotate one detector, the correlation changes in a way that quantum mechanics predicts precisely. And the crucial result. When you calculate a certain combination of correlations from different detector angles, you get a number that exceeds the limit set by Bell's inequality. You cannot explain these correlations by assuming the photons had definite polarizations all along, set at the moment they were created. No pre-existing properties can account for the strength of the correlations. The correlations are stronger than any local realistic theory allows. This has been done not just in labs, but across cities. Experiments have been performed with the two detectors separated by hundreds of kilometers, connected by fiber optic cables. with each measurement event separated in a way that no light speed signal from one detector could reach the other in time to influence the result. The correlations persist. They are not caused by any signal traveling between the detectors. They are a feature of the entanglement itself. The most rigorous experiments performed in recent years have closed the major loopholes that earlier experiments left open. The detection loophole, the possibility that the detectors were only catching a biased sample of photons. The locality loophole, the possibility that information about one detector's setting could have reached the other detector before the measurement. In 2015, 3 independent groups working in Delft, Vienna, and Boulder performed loophole-free Bell tests. They closed all major loopholes simultaneously for the first time. The result was the same. Bell's inequality is violated. Local realism is ruled out. This is not a matter of interpretation. The violation of Bell's inequality is an experimental fact, as solid as any fact in physics. What it means for our picture of reality is a matter of interpretation. But that it happens, there is no doubt. Now, I want to talk about one more aspect of entanglement that often gets overlooked in popular discussions. Entanglement is not rare. It is not a delicate, exotic phenomenon that requires special laboratory conditions to produce. Entanglement is everywhere. In fact, entanglement is the generic condition of quantum systems that have interacted. Anytime 2 particles interact, they become entangled. When a photon bounces off a wall, the photon and the atoms of the wall become entangled. When 2 atoms collide in a gas, they become entangled. When a particle is measured by a detector, the particle and the detector become entangled. In a large complex system, like a gas or a solid or a living creature, the entanglement spreads rapidly. Every particle becomes entangled with every other particle it interacts with, and through those particles, with the particles they have interacted with, until the entanglement spreads throughout the entire system and into the environment. This spreading of entanglement is the process that physicists call decoherence. And decoherence is the reason why quantum effects like superposition and entanglement are not visible in everyday life. When a particle becomes entangled with the environment, its quantum state becomes correlated with the states of an astronomical number of environmental particles. The superposition does not disappear, but the different branches of the superposition become entangled with different orthogonal states of the environment. They no longer interfere with each other. The quantum coherence is lost, washed out by the entanglement with the environment. From the perspective of any observer who does not track all the environmental particles, the particle appears to have acquired a definite state. The superposition looks like it has collapsed, even though in the full quantum state of the system, plus the environment, it has not. Decoherence happens extraordinarily rapidly for macroscopic objects. A dust particle in air loses quantum coherence in roughly 10 to the minus 31st power seconds. For any object you can see with the naked eye, coherence is lost almost instantaneously. This is why you do not see cats in superpositions, not because large objects are exempt from quantum mechanics, but because their interaction with the environment destroys quantum coherence before it can produce observable quantum effects. But at the microscopic level, before decoherence has had time to act, entanglement is universal. It is the rule, not the exception. And here is the astonishing implication. The entire universe is one enormous entangled system. Every particle that has ever interacted with another particle is entangled with it. Every atom in your body is entangled with the atoms it has interacted with during your lifetime. Every photon emitted by the sun and absorbed by the earth has entangled the sun and the earth. Over the history of the universe, through billions of years of interactions, everything has become entangled with everything else. The universe, at the quantum level, is not a collection of separate things. It is a single, vast quantum state. The separateness of objects is an approximate, emergent feature that appears when you zoom out and ignore most of the entanglement. At the fundamental level, the universe does not have parts. It has a single, unified quantum description that cannot be factored into independent pieces. This is what entanglement is ultimately telling us, not just that 2 particles can be correlated across a distance, but that the universe, at its deepest level, is whole, undivided, a single thing, not a collection of things. The philosopher David Bohm called this the implicate order. The idea that beneath the explicit separate world we observe, there is an implicate, enfolded order in which everything is connected to everything else. He did not have the mathematics of quantum entanglement fully worked out when he proposed this idea, but he was pointing at something that modern physics has confirmed in precise, quantitative detail. The separateness you experience is real. You are here, and I am there. This particle is here, and that particle is there. But this separateness is not the deepest truth about the universe. The deepest truth is that everything is connected. That what happens here affects what is there in ways that cannot be fully captured by thinking about separate objects in separate places. This is not mysticism, it is physics. Experimentally confirmed, mathematically precise physics. But it is physics that points toward a picture of reality that is, in its deepest structure, fundamentally different from the world of separate, local objects that common sense presents to us. Before we close, let me say something about where entanglement research is heading today, because it is not just a philosophical curiosity, it is becoming a technology. Quantum cryptography uses entanglement to create communication channels that are provably secure if two parties share entangled particles and use them to generate encryption keys. Any attempt by an eavesdropper to intercept the key will disturb the entanglement in a detectable way. The security is guaranteed not by the difficulty of breaking a code, but by the laws of physics themselves. Several quantum cryptography networks are already in operation around the world, including networks spanning hundreds of kilometers of fiber optic cable. Quantum computing uses entanglement as a computational resource. A quantum computer can store information in quantum states and process it in ways that exploit superposition and entanglement to perform certain calculations exponentially faster than any classical computer could. Quantum computers are still in their early stages, but they have already demonstrated quantum advantage, the ability to solve specific problems faster than classical computers, for carefully chosen tasks. As the technology matures, quantum computers are expected to revolutionize cryptography, drug discovery, materials science, and optimization problems. Quantum teleportation uses entanglement to transfer the quantum state of one particle to another, distant particle. Not the particle itself, only its state. And the process requires a classical communication channel in addition to the entanglement, so no information travels faster than light. But quantum teleportation has been demonstrated experimentally over distances of hundreds of kilometers, and it is a key ingredient in proposed quantum networks that could connect quantum computers across large distances. Quantum sensing uses entanglement to make measurements of extraordinary precision beyond what is possible with classical instruments. Quantum-enhanced sensors may one day detect gravitational waves with higher sensitivity than current detectors, map the magnetic fields in the brain with unprecedented resolution, and search for dark matter and other exotic particles with new levels of sensitivity. All of these technologies exist because entanglement is real. Because Einstein was wrong, and the universe really does contain non-local correlations that cannot be explained by any local realistic theory. The weirdness of quantum mechanics is not a flaw, it is a resource. The universe's spookiness is something we are learning to use. And underlying all of it is the same fundamental strangeness we have been exploring tonight. Two particles sharing a quantum state. A measurement here, an instant correlation there. A universe that, at its deepest level, is not a collection of separate things, but a single, entangled whole. Let me leave you with one final thought. You are sitting here tonight, listening to these words. You are made of atoms. Those atoms are made of electrons and protons and neutrons. Those particles have been interacting with other particles your entire life, with the air around you, with the light falling on you, with the food you have eaten and the water you have drunk. Through every one of those interactions, entanglement has spread. You are entangled with your environment. Your environment is entangled with the wider world. The wider world is entangled with the universe. At the quantum level, you are not a separate thing. You are a region of the universe's quantum state that has a particular kind of complexity, a complexity that somehow produces the experience of being a separate, bounded, conscious creature. But the separateness is approximate, the boundaries are fuzzy, and at the deepest level of description, You are not separate from the universe at all. You are part of a single, vast, entangled whole that has been evolving since the first moments after the Big Bang. Einstein called entanglement spooky action at a distance. He meant it as a criticism, a reductio ad absurdum. Surely, he was saying, a theory that requires this must be wrong. But the theory is not wrong. The spookiness is real. And sitting with that fact, really sitting with it, is one of the most extraordinary experiences that physics can offer. The universe is stranger than common sense allows. Reality does not exist independently of observation, at least not in the way we assumed. Things that are separated by vast distances are connected in ways that no signal, no matter how fast, could explain. We do not know exactly what this means for the nature of reality. We are still arguing about it. The debate between the interpretations of quantum mechanics is one of the most productive and unresolved debates in the history of science. But we know this. The universe is entangled. Everything is connected to everything else in ways that are real, measurable, and still, after nearly a century of quantum mechanics, genuinely astonishing. Good night. Wait, before we truly close, I want to go back and spend more time with something we moved through quickly. Because Bell's theorem deserves more than a paragraph. It is one of the most profound results in the history of science, and I want you to feel exactly how it works, because once you see it, the strangeness of entanglement becomes impossible to dismiss. Let me walk you through a simplified version of the Bell argument, not the full mathematical derivation, but the core logical structure, because the logic itself is the thing. The logic is what makes Bell's theorem so devastating to the hidden variable picture. Suppose you have two detectors, one for each entangled particle. Each detector can be set to one of three orientations. Let us call them A, B, and C. When a particle reaches a detector, the detector measures the spin of the particle along the chosen orientation, and the result is either +1 or -1, up or down. Now, suppose Einstein was right. Suppose each particle carries hidden variables, predetermined instructions for what result to give at each detector orientation. The particle going left carries some hidden instruction set, and the particle going right carries the matching hidden instruction set, determined at the moment the two particles were created together. These hidden variables are set in advance. They determine the outcome of any measurement before the measurement happens. Because the particles are created together with matching hidden variables, there will be correlations between the results at the two detectors. That is expected and uncontroversial. The question is how strong those correlations can be. Here is where Bell's argument comes in. With three possible orientations and two possible results, each particle's hidden variable instruction set is one of 8 possible combinations. For each combination, you can calculate what the measurement results would be at each pair of detector settings. And when you do that calculation, you find a constraint, a mathematical inequality that any local hidden variable theory must satisfy. The specific constraint Bell derived is this: the number of times the two detectors agree when set to different orientations cannot exceed a certain value relative to the total number of measurements. This is Bell's inequality. It is a hard mathematical limit, valid for any local realistic theory, regardless of the details of the hidden variables. But quantum mechanics predicts correlations that exceed this limit. When the detector orientations are chosen to be the angles that maximize the quantum correlation, quantum mechanics predicts measurement results that violate Bell's inequality, more agreements than any local hidden variable theory can produce. You do not have to trust the theory. You can measure it, set up the experiment, run it thousands of times, count the agreements, compare the count to Bell's inequality. The experiments have been done. The count exceeds Bell's limit every time, without exception. This means no local hidden variable theory can reproduce the quantum correlations. Any theory that says the particles have definite pre-existing properties must either be wrong in its predictions, which rules it out, or it must allow for faster-than-light influences, which makes it non-local. There is no escape. The universe violates Bell's inequality. That is a fact, and every fact has consequences. Now, I want to spend time with what has been called the measurement problem, because it is at the heart of why entanglement is so philosophically disturbing, and we have not given it the attention it deserves. The measurement problem is this: Quantum mechanics describes a system evolving smoothly and continuously according to the Schrödinger equation, which is perfectly deterministic and perfectly reversible. But when a measurement happens, something discontinuous occurs. The superposition collapses to a definite outcome. The smooth, deterministic evolution is interrupted by a random, irreversible jump. The problem is that the Schrödinger equation never tells you when to apply this collapse. The equation just keeps evolving everything smoothly. But measurements definitely seem to produce definite outcomes. You get a specific result, not a superposition of results. So, where does the collapse come from? When exactly does it happen? What counts as a measurement? These questions are at the center of the foundational debate about quantum mechanics, and they connect directly to entanglement. Because entanglement spreads. When a particle in a superposition interacts with a measuring device, the superposition does not collapse. Instead, the measuring device becomes entangled with the particle. The combined system of particle plus measuring device is now in a superposition. If a physicist then looks at the measuring device, the physicist becomes entangled with the system. The superposition has spread to include the physicist. If you take the Schrödinger equation seriously and apply it to everything including the measuring device and the physicist, you never get a collapse. You just get an ever larger superposition. The particle is in a superposition of spin up and spin down. The measuring device is in a superposition of reading up and reading down. The physicist is in a superposition of having seen up and having seen down. The room is in a superposition, the building, the planet, everything. And yet the physicist reports seeing a definite result, not a superposition, a definite result. So either the Schrödinger equation breaks down somewhere and collapse is a real physical process, a modification of quantum mechanics that we have not discovered yet, or the apparently definite result is somehow consistent with the superposition persisting, which is the many worlds view, or there is something special about the observer or consciousness that causes collapse, which is the most controversial suggestion and the least favored by physicists today. John von Neumann, who formalized quantum mechanics mathematically in the 1930s, drew a chain of entanglement from the particle being measured all the way up to the observer's consciousness, and suggested that the collapse happened somewhere in that chain. He could not specify where, and nobody since has been able to either, in any fully satisfying way. This is not an idle philosophical puzzle. It is a real gap in our understanding. Quantum mechanics tells us how to calculate probabilities of measurement outcomes. It does not tell us, in a physically precise way, what a measurement is or why it produces definite outcomes. Filling this gap is one of the most important unsolved problems in the foundations of physics. And entanglement makes the gap impossible to ignore, because entanglement demonstrates concretely that quantum correlations are real and non-local, that the superposition does spread, that the measuring device and the observer really do become entangled with the system they are observing. Pretending that collapse is just a useful approximation, a way of updating your knowledge, becomes harder and harder to maintain in the face of experiments that show entanglement is a real, physical phenomenon with real, measurable consequences. Let me now turn to something more recent. Because in the last 2 decades, understanding of entanglement has taken a dramatic new turn, driven by developments in quantum information theory, string theory, and the study of black holes. In 1997, Juan Maldacena, a physicist at the Institute for Advanced Study in Princeton, discovered a remarkable mathematical duality. He found that a certain string theory in a particular curved spacetime was exactly equivalent to a quantum field theory living on the boundary of that spacetime. This is the ADS/CFT correspondence we mentioned earlier, and one of its most striking features is that the geometry of the bulk spacetime, the distances between points, the curvature, the structure of space, is encoded in the entanglement structure of the boundary quantum theory. Regions of the boundary theory that are highly entangled correspond to regions of the bulk spacetime that are nearby. Regions that are not entangled correspond to regions that are far apart. The geometry of space, in other words, is built from entanglement. This led physicist Mark van Ramsdonk and others to propose that entanglement is not just a feature of quantum mechanics, but a fundamental ingredient in the structure of spacetime. Remove the entanglement from a quantum state, and the corresponding spacetime falls apart, literally. The geometry becomes disconnected, space tears, the metric becomes ill-defined. In one famous thought experiment, consider two entangled black holes, one on each side of the universe. In the language of ADS/CFT, these two entangled black holes correspond to a space-time that has a wormhole connecting them, a bridge through space-time that goes from one black hole to the other. The wormhole is the geometric manifestation of the entanglement. This ER equals EPR conjecture, put forward by Juan Maldacena and Leonard Susskind in 2013, states that every pair of entangled particles is connected by a Planck scale wormhole. Einstein-Rosen bridges, the technical name for wormholes, are equivalent to Einstein-Podolsky-Rosen correlations, the technical name for entanglement. ER equals EPR. If this conjecture is right, and it is still being developed and tested in the theoretical physics community, then entanglement is not just a strange feature of quantum mechanics. It is the physical mechanism by which space-time is constructed. The quantum entanglement between particles is the same thing as the geometric connectivity of space-time. The fabric of space is woven from the correlations between quantum systems. This is a breathtaking idea. It suggests that the apparent mystery of entanglement, how can two distant particles be so deeply correlated, has a geometric answer. They are correlated because they are connected, not by a signal traveling through space, but by a wormhole in the very structure of space-time. The non-locality of entanglement is not mysterious once you understand that space itself is built from entanglement. The two particles are far apart in the space you can navigate with a spaceship, but they are also nearby in a deeper geometric sense that the ordinary spatial distance does not capture. And this deeper geometry, this web of connections that space is built from, is made of quantum entanglement. We are still working this out. The ER equals EPR conjecture is not proven. ADS/CFT is a mathematical duality discovered in a specific theoretical context and has not been directly verified experimentally. But these ideas are guiding some of the most exciting research in theoretical physics today. Research into quantum gravity, the black hole information paradox, and the emergence of spacetime from quantum mechanics. And they suggest that when you look at two entangled particles, you are not just looking at a weird quantum correlation. You are looking at the building blocks of space itself. You are seeing the universe constructing its own geometry, one entangled pair at a time. I also want to say something about the human story of entanglement, because the physics does not exist in a vacuum. It was discovered by specific people, in specific historical circumstances, and the human story matters. Einstein died in 1955, still convinced that quantum mechanics was incomplete. He never wavered in his belief that the theory was missing something, that hidden variables existed, that God does not play dice with the universe. He spent the last decades of his life working on unified field theories, trying to find a deeper framework that would make quantum mechanics unnecessary, or at least subsume it into something more classical. He did not succeed. And the Bell experiments, which definitively refuted the hidden variable hypothesis, came after his death. He never knew he was wrong. John Bell, who derived the inequality that made it possible to test Einstein's hypothesis, was a fascinating figure. He worked on accelerator physics for CERN professionally, doing the calculations that kept the particle beams running. His work on the foundations of quantum mechanics was done in his spare time, almost as a hobby, because CERN was not paying him to think about philosophy. He was deeply troubled by the conventional dismissal of foundational questions in physics, the attitude that shut up and calculate is all the discipline requires. He wanted to understand what quantum mechanics was actually saying about the world, and his inequality was the most important contribution to that understanding in half a century. Bell died in 1990 from a cerebral hemorrhage just days after being notified that he had been nominated for the Nobel Prize. He never received it. The Nobel Prize is not awarded posthumously, and the committee had not yet acted on the nomination when he died. His inequality, one of the most important results in the history of physics, was never recognized by the Nobel Committee during his lifetime. Alain Aspect, who performed the first convincing experimental tests of Bell's inequality in the early 1980s, was awarded the Nobel Prize in Physics in 2022, along with John Clauser and Anton Zeilinger, The prize citation was for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. 40 years after the experiments were performed, the Nobel Committee finally recognized how important they were. The story of entanglement is a story of patience and persistence, of physicists who cared about the foundational questions when the mainstream of their discipline did not, who kept asking what quantum mechanics meant, what reality was like in between measurements, what the non-local correlations were telling us about the universe, and who eventually, through careful experiment and deep mathematical work, found that those questions led not just to philosophical insight, but to a new technology and a new understanding of the structure of space-time. Physics rewards the people who refuse to stop asking why. Now, let us end where we began. Two particles, created together in a special quantum state, separated, sent in opposite directions. One measured here, the other measured there. The results correlated in a way that no local hidden variable theory can explain. This is real. This happens in laboratories around the world, every day. It has been confirmed with every possible experimental precaution. It is as solid as any fact in physics. What it means is still, in some ways, being worked out. The interpretations debate is alive. The ER equals EPR conjecture is being developed. The measurement problem is unsolved. The nature of quantum reality, what the universe is actually like in between measurements, remains genuinely open. But some things are clear. The universe is non-local in a way that Einstein refused to accept. Reality does not consist of separate local objects with definite properties. Something about the deepest level of physics is fundamentally different from the picture common sense presents to us. And the something that is different, the thing that makes the universe so strange, is also the thing that makes it so deeply, inescapably connected. Everything is entangled with everything else. The separateness of the world is approximate, emergent, real at the level of our experience, but not at the level of the fundamental description. You are made of particles that have been interacting and entangling for billions of years. You are not separate from the universe. You are the universe, looking at itself, entangled with itself, discovering slowly and with great effort how strange and how unified it actually is. Einstein called it spooky action at a distance. He meant it as an insult to the theory, but the spookiness is real, and it is, in its own way, beautiful. But I want to go even further tonight, because there are dimensions of entanglement that we have not yet explored, and they deserve your attention. Let me tell you about something called quantum teleportation, not the science fiction version, where people are disassembled and reassembled elsewhere. The real version, which is stranger in its own way. In 1993, a group of physicists, including Charles Bennett and William Wooters, showed theoretically that it is possible to transfer the complete quantum state of one particle to another particle, across any distance using a shared entangled pair as a resource. The paper caused a sensation. It was called quantum teleportation. Here is how it works. Alice has a particle in some quantum state. She wants to transfer that quantum state to Bob, who is somewhere far away. Alice and Bob each have one particle of an entangled pair, created earlier and distributed between them. Alice performs a special measurement on her particle and her half of the entangled pair simultaneously. This measurement produces a result, which is random and gives Alice no information about the original state of her particle. But the measurement also does something to Bob's particle, instantly because of the entanglement. It puts Bob's particle into a state that is related to the original state of Alice's particle by a simple transformation. Alice sends the result of her measurement to Bob through an ordinary classical channel. Bob uses this information to apply the right transformation to his particle. And when he does, his particle is now in exactly the quantum state that Alice's original particle was in. The original particle's state has been teleported to Bob's particle. The quantum state is now there, not here. And here's the beautiful part. Alice's original particle no longer has that state. The measurement she performed destroyed it. The state was transferred, not copied. This is necessarily so because of the no-cloning theorem, which says you cannot copy an unknown quantum state. You can only move it. Quantum teleportation has been demonstrated experimentally. In 1997, Anton Zeilinger's group in Vienna teleported the quantum state of a photon across several meters of lab. Since then, the distances have grown dramatically. Quantum states have been teleported between the Canary Islands across a distance of 143 kilometers of open air. In 2017, a Chinese satellite called Micius teleported quantum states from the ground to the satellite, demonstrating teleportation over more than 1,200 kilometers. This is not science fiction, it is happening, and it is powered entirely by entanglement. But notice something crucial. The teleportation requires Alice to send her classical measurement result to Bob. That classical communication travels at, or below, the speed of light. No information is transferred faster than light. The quantum state cannot arrive at Bob until after the classical message does. Entanglement enables the teleportation, but it does not allow it to happen faster than light. This is a deep feature of quantum mechanics. Entanglement allows things that would otherwise be impossible. It allows the transfer of a quantum state without physically moving the particle. It allows correlations between distant measurements that no classical communication could produce, but it never allows information to propagate faster than light. The non-locality is always constrained in exactly the right way to avoid violating relativity. The universe seems to have found a way to be maximally strange while remaining consistent with the principles we know to be true. It threads the needle between being local enough for relativity and being non-local enough for entanglement. And how it manages to do both simultaneously is one of the deepest and most beautiful features of the physical world. Now, I want to take you somewhere that most discussions of entanglement never go. I want to talk about what entanglement means for our understanding of complexity and the origin of classical physics. We live in a classical world. The objects around you have definite positions, definite velocities, definite properties. The desk under your hands is not in a superposition. The chair you are sitting in is not entangled with the chair across the room in any observable way. The world looks classical. It behaves classically. And yet it is made of quantum particles, which are in superpositions and are entangled. How does the classical world emerge from the quantum world? How do definite properties appear from a sea of indefiniteness? How does the solid, local, separate-seeming reality of everyday life arise from the non-local, entangled, superposition-ridden quantum reality underneath? This is the question of the quantum classical transition, and entanglement is at its heart. The answer, as we touched on earlier, involves decoherence. But let us go deeper into what decoherence actually does and why it matters. Consider a particle in a superposition of two positions, left and right. As long as the particle is isolated from its environment, the superposition persists. The particle is genuinely in both positions. If you bring the two branches of the superposition back together, they interfere. You can see the interference pattern. The superposition is real and observable. Now, let the particle interact with a single photon. The photon bounces off the particle, and in doing so, it becomes entangled with the particle. The state of the photon now carries information about which position the particle was in when the photon bounced off it. The particle and the photon are now in an entangled state. If you now try to see the interference between the two branches of the particle's superposition, you find that the interference is reduced. The photon has essentially measured the particle's position, and measuring destroys the superposition. The particle appears to have a definite position, even though the Schrödinger equation has not collapsed anything. The superposition still exists in the full quantum state of particle plus photon, but the particle's reduced state, the description of just the particle ignoring the photon, looks like a mixture of definite positions rather than a superposition. In the real world, particles do not interact with just one photon. They interact with vast numbers of environmental particles, air molecules, photons from the background radiation, vibrations in the substrate. Every interaction entangles the particle with another environmental degree of freedom. Every environmental degree of freedom carries away a little bit of the phase information that makes quantum interference visible. After a very short time, the particle has become entangled with so many environmental particles that the interference between different branches of its superposition is completely washed out. The superposition still exists in the full quantum state of the universe. But it is completely invisible from the perspective of anyone who is not tracking all the environmental particles simultaneously. And since tracking all the environmental particles simultaneously is impossible for any realistic observer, the particle effectively has a definite state. This is why the classical world looks classical, not because quantum mechanics stops applying at some scale, not because there is a physical collapse of the wave function, but because entanglement with the environment makes the quantum interference unobservable. The classical world is quantum mechanics seen through the lens of inevitable, ubiquitous entanglement with a complex environment. And here is the profound implication. The classical world you experience, the solid, separate, definite-seeming reality of everyday life, is entirely a product of entanglement, not the absence of entanglement, its overwhelming presence. Entanglement is what makes the world look classical. This is one of the most remarkable insights of 20th century physics, and it is still not widely appreciated outside of specialist circles. The quantum and the classical are not two different kinds of reality. They are the same reality seen at different scales of entanglement. The quantum reality is the full description. The classical reality is what quantum reality looks like when it is so thoroughly entangled with its environment that all quantum interference is suppressed. Let me now tell you about a thought experiment that sits at the intersection of entanglement, consciousness, and the nature of reality. It is called Wigner's Friend, and it was proposed by the physicist Eugene Wigner in 1961. Wigner imagines the following scenario. His friend goes into a laboratory and performs a measurement on a quantum system, say an electron whose spin is in a superposition of up and down. The friend observes the result. From the friend's perspective, the superposition has collapsed. The electron is either up or down, and the friend knows which. But now, Wigner, who is outside the laboratory and has not communicated with his friend, asks, what is the quantum state of the system inside the laboratory? If Wigner applies the Schrödinger equation to everything inside the laboratory, including the electron, the measuring device, and his friend, he gets a superposition. The laboratory is in a state where, in one branch, the electron is up and the friend has seen up, and in another branch, the electron is down and the friend has seen down. From Wigner's perspective, the superposition has not collapsed. But from the friend's perspective, it has. The friend has a definite experience. The friend knows the result. How can the friend have a definite experience while Wigner's description says the friend is in a superposition? This is Wigner's friend paradox. It seems to suggest that quantum mechanics assigns different realities to different observers, that what counts as a definite fact depends on who is asking. That reality is observer-dependent in a fundamental sense. This is not just a thought experiment anymore. In 2019, physicists at the Heriot-Watt University in Edinburgh performed an experiment inspired by Wigner's friend using photons. They showed that the predictions of quantum mechanics really do assign different, mutually inconsistent facts to different observers in certain experimental scenarios. The results were consistent with quantum mechanics, and inconsistent with a world in which objective, observer-independent facts exist at all times. This is perhaps the most disturbing implication of quantum mechanics. Not just that particles do not have definite properties before measurement, but that what counts as a definite fact may depend on who is measuring. That reality, in the quantum sense, may not be objective. That different observers with different information and different measurement histories may genuinely have different, incompatible descriptions of what has happened. Some physicists take this seriously and are exploring what it means for our concept of reality, knowledge, and objectivity. Others think it points to the need for a better formulation of quantum mechanics, one that does not lead to observer-dependent facts. Others think it is simply showing us that quantum mechanics is a probabilistic tool for predicting the outcomes of measurements, not a description of what reality is like in between measurements, and that asking what reality is like in between measurements is asking the wrong kind of question. None of these responses is fully satisfying. The Wigner's friend paradox, like the measurement problem and the Bell inequalities, is telling us that the conceptual framework we use to think about reality is inadequate for the quantum world, that new concepts are needed, that the revolution begun by Bohr and Heisenberg and Einstein in the 1920s is not finished. that the deepest implications of quantum mechanics for our picture of reality are still being worked out. This is what makes quantum mechanics so inexhaustible as a subject. Nearly 100 years after the theory was formulated, it is still generating new experimental results, new theoretical insights, and new philosophical puzzles. It is still, in some deep sense, not understood. Not because the formalism is unclear. The formalism is extraordinarily precise and extraordinarily successful. But because the formalism points at a reality that our concepts are not yet equipped to describe. Entanglement is at the center of all of it. The strange correlations between distant particles, the non-local structure of the quantum state, the way that measurement here affects outcomes there, the way that the universe resists any attempt to describe it as a collection of separate, local things with definite properties. All of this is entanglement, and entanglement is telling us something about the universe that we are still learning to hear. Let me close with a thought about what it means to live in an entangled universe. Every morning, you wake up, and the world seems solid, definite, separate. The cup is on the table, the light comes through the window, the ground is under your feet. Everything seems to be where it is, with the properties it has, independently of whether you are looking at it. Quantum mechanics says this picture is a very good approximation and an incomplete description. The cup is not separate from the table. The photons from the window have entangled themselves with every surface they have touched. Your body is not separate from the air. The electrons in your lungs and the oxygen molecules they bind to have exchanged quantum information have entangled, have become part of a shared quantum state that spans both. At the level of individual particles, there is no clean separation. Everything is connected. The separateness is an emergent property, arising from the way entanglement with the environment suppresses quantum interference and makes the world look classical. The solid, definite, local world is real. But it is not fundamental. Underneath it is something more fluid, more connected, more strange. Two particles, entangled, separated by any distance you choose, correlated in ways that no local explanation can account for. This is the universe telling you something about itself, something it has been true of since the first particles interacted after the Big Bang, something that will be true until the last particles stop interacting at the end of time. The universe is one, not in some vague, poetic sense, in a precise, measurable, experimentally confirmed, mathematically rigorous sense. The quantum state of the universe cannot be factored into independent pieces. Everything that has ever interacted is, at some level, still connected. The interactions leave traces in the form of entanglement. The traces persist. The universe remembers every connection it has ever made. You are part of that memory. Your atoms are entangled with the atoms they have interacted with. Those atoms are entangled with others. The connections stretch back and outward through time and space, to the earliest moments of the universe, to the last moments of stellar explosions that forged your atoms, to the first moments of the Earth forming, to the first moments of life arising, to every breath you have taken and every photon that has ever touched your skin. You are not alone in the universe. You could not be, even if you tried. Entanglement makes it impossible. Einstein called it spooky. He was right that it is strange. He was wrong that it does not exist. It exists. It is real. And it is perhaps the most important fact about the universe that physics has discovered in the last 100 years. But before you sleep, let me give you one more layer. Something that brings everything together and shows you entanglement not as an isolated curiosity, but as a thread running through the whole of modern physics. It is the story of quantum information theory. For most of the 20th century, information was treated as a classical concept. A bit is a 0 or a 1. Shannon's theory of information, developed in the 1940s, underpins all modern communication technology. But it treated the physical nature of information as irrelevant. Quantum mechanics changed this. Information is physical, and quantum bits, or qubits, can be entangled in ways classical bits cannot. Entangled qubits can perform computations exponentially faster than classical computers for certain problems. Peter Shor showed in 1994 that a quantum computer could factor large numbers exponentially faster than any known classical algorithm, threatening the encryption that secures the modern internet. The fundamental resource in quantum computing is entanglement. The power of a quantum computer comes from its ability to maintain and manipulate large entangled states. When the computation is done, interference between different paths amplifies the right answer and cancels the wrong ones. This requires maintaining coherent entanglement among all the qubits throughout the computation. Companies including Google, IBM, and IonQ have built quantum processors with dozens to hundreds of qubits. In 2019, Google's processor Sycamore performed a specific computation in 200 seconds that would have taken classical supercomputers thousands of years, a landmark demonstration that entanglement gives real, measurable computational power. And all of it runs on the phenomenon Einstein called a defect in the theory. At the cosmological scale, the story is just as astonishing. During inflation, the universe expanded by an enormous factor in an extraordinarily short time. Quantum fluctuations, entangled pairs of virtual particles, were stretched to cosmic scales by this expansion. These stretched quantum fluctuations became the seeds of all large-scale structure in the universe. The galaxies, the galaxy clusters, the vast filaments and voids of the cosmic web, all trace back to quantum entanglement in the first fraction of a second after the Big Bang. The pattern of temperature fluctuations in the cosmic microwave background matches the predictions of quantum field theory in an expanding universe with stunning precision. The structure of everything you can see in the night sky carries the imprint of quantum entanglement from the earliest moments of time. You exist in this precise location in the universe because of where quantum fluctuations landed during inflation. Your existence is, at some level of description, an outcome of a cosmic quantum measurement. This is not metaphor, this is physics. Two particles, entangled, separated by any distance, correlated beyond what any local realistic theory can explain. What it means for the nature of reality, we are still working out. The interpretations are many, the debates are alive, the foundational questions are not resolved, but the fact itself is clear. The universe is not made of separate local things. It is made of connections, of correlations, of entanglement. The separateness you experience is real, but it is not the deepest truth. The deepest truth is that everything is connected, that what happens here is correlated with what happens there, in ways that no signal can explain, that no classical theory can reproduce, that nothing in common sense prepares you for. Einstein called it spooky. He was right about the spookiness. He was wrong to think it meant the theory was defective. The theory is not defective. The universe is just stranger than he was willing to accept. Stranger, and more connected, more whole, more beautiful. Let me sit with you for a moment longer, because there is something about entanglement that I think deserves to be said slowly, carefully, without rushing toward the next idea. When you learn about entanglement for the first time, there is a temptation to explain it away. To say, yes, it is strange, but it does not really affect my life. The particles in my coffee cup are not behaving in any noticeable quantum way. The world around me looks classical, and that is what matters. And it is true that your coffee cup behaves classically. Decoherence ensures that. The quantum weirdness is suppressed at the scales of everyday life, and the physics you encounter in daily experience is safely Newtonian. But the fact that quantum effects are suppressed at everyday scales is not the same as saying they are absent or unimportant. The quantum world underpins the classical world. The properties of matter that you rely on every moment of every day are quantum properties. The reason metals conduct electricity, the reason glass is transparent, the reason your hand is solid and cannot pass through the table, all of these are quantum phenomena. The stability of atoms, the structure of the periodic table, the way chemical bonds form, quantum mechanics all the way down. And entanglement, specifically, underpins several things you might not expect. Take the phenomenon of superconductivity. In certain materials, cooled to very low temperatures, electrical resistance vanishes completely. Current that flows through the material without losing any energy. This is one of the most remarkable phenomena in condensed matter physics, and it has enormously practical applications. MRI machines, particle accelerator magnets, and potentially future power transmission systems all use or are expected to use superconducting materials. Superconductivity arises because electrons in a superconductor form entangled pairs, called Cooper pairs, that move through the material in a coordinated quantum state. The pairing is mediated by the vibrations of the crystal lattice, and the entire macroscopic superconducting state, the flow of current without resistance, is a consequence of millions of Cooper pairs all sharing the same quantum state, all moving in lockstep, all entangled into a single collective quantum entity that extends throughout the material. A superconductor is a macroscopic quantum state, an object you can hold in your hand that is in a coherent, entangled quantum state. Its remarkable electrical properties are a direct consequence of quantum entanglement at the macroscopic scale. Similar phenomena appear in other condensed matter systems, superfluids, which flow without viscosity, Bose-Einstein condensates, which are clouds of atoms all collapsed into the same quantum state at temperatures near absolute zero, quantum Hall states, which have extraordinarily precise and robust electrical properties tied to the topology of their quantum state. All of these are examples of entanglement operating at macroscopic scales, producing phenomena that have no classical explanation. And then there is something even closer to home. There is growing evidence that biology exploits quantum mechanics, including entanglement, in ways that go beyond anything we previously suspected. The most studied example is photosynthesis. When a photon is absorbed by a photosynthetic complex, the molecular machinery in plant cells and bacteria that captures sunlight and converts it to chemical energy. The energy must be transferred from the point of absorption to the reaction center where it can drive chemistry. This transfer happens with extraordinary efficiency. Almost every photon that is absorbed results in a reaction. Almost none of the energy is wasted. For decades, scientists assumed this happened by classical energy transfer, the energy bouncing from molecule to molecule until it reached the reaction center. But experiments in 2007 revealed something astonishing. The energy transfer in photosynthesis involves quantum coherence. The energy does not hop from molecule to molecule classically. It spreads as a quantum superposition across multiple pathways simultaneously. It samples multiple routes at once, and, by quantum interference, finds the most efficient path to the reaction center. Whether genuine entanglement between different parts of the photosynthetic complex is involved, and whether the quantum effects persist long enough in the warm, wet biological environment to actually enhance efficiency, is still debated. The story turned out to be more complicated than initial reports suggested, but the evidence that quantum coherence plays a role in some biological processes is substantial, and the question of how extensively biology exploits quantum mechanics is an active area of research. There are also proposals that quantum mechanics plays a role in bird navigation. Certain birds can sense the Earth's magnetic field and use it to navigate during migration. The proposed mechanism involves a quantum process called the radical pair mechanism, in which entangled electron pairs and molecules in the bird's eye are sensitive to magnetic fields in a way that depends on their quantum state. Quantum entanglement in the bird's eye might be helping it navigate. This would mean that entanglement is not just a laboratory curiosity or a feature of exotic condensed matter systems. It would mean that evolution has discovered and exploited quantum entanglement as a biological resource. That billions of years of natural selection have found ways to use the strangeness of quantum mechanics to make life work better. We do not yet know for certain whether this is true. The quantum biology field is young, and the evidence is still being gathered, but the possibility is extraordinary. The universe's quantum nature, the entanglement and superposition that Einstein found so troubling, may be a tool that life uses without knowing it, a feature of reality that biology discovered before physics did. This is one of the frontiers of science, and it connects directly to the oldest and deepest question about entanglement, not what it is technically, but what it means. What it tells us about the universe we live in, about the nature of reality, about the relationship between the quantum and the classical, between the microscopic and the macroscopic, between the physical and the biological and the conscious. We are, as I said earlier, still working this out. The quantum revolution that began in the 1920s has not ended. It is continuing, expanding into new domains, raising new questions, producing new technologies and new insights and new mysteries. And at the center of it, threading through all of it, is entanglement. The spooky action at a distance that Einstein refused to accept. The phenomenon that Bell showed could be tested. The result that experiments confirmed again and again. The resource that quantum computers exploit. The foundation on which the quantum internet will be built. The mechanism by which cosmic structure was seeded. The possible basis of certain biological processes. The ingredient, perhaps, from which space-time itself is woven. Entanglement. Two particles, connected across any distance. The universe, refusing to be separated into truly independent parts. I want to give you one final image to carry tonight. One that brings all of this down from the abstract and into something you can feel. Think about the last time you looked into someone else's eyes. Truly looked. Not a glance, not a passing acknowledgement, but a moment of genuine connection where you felt, however briefly, that you were seeing something real in another person, and that they were seeing something real in you. That moment of connection, that sense of genuine contact between two separate consciousnesses, is mediated entirely by physics. Photons left your retinal cells, scattered off the other person's face, bounced back into your eyes. Neurons fired in patterns that have been shaped by billions of years of evolution. Electrochemical signals propagated through your nervous system. And somewhere in that extraordinarily complex cascade of physical processes, the experience of connection arose. Every photon in that exchange was a quantum particle. Every electron in every neuron that fired was a quantum particle. Every chemical bond involved in the signaling was a quantum interaction. The entire experience of looking into someone else's eyes and feeling genuine connection is, at its foundation, a quantum event, built from quantum particles interacting according to quantum laws, entangling with each other and with the environment, producing, through the extraordinary complexity of biological neural architecture, the experience of being present with another person. The connection you felt in that moment is, in some sense, a macroscopic manifestation of the same physics that produces entanglement between two particles in a laboratory. The same fundamental rules, the same quantum interactions, operating at vastly different scales of complexity, producing vastly different but deeply related phenomena. Entanglement in the lab. Connection in the world. This is not a mystical claim, it is a physical one, and it suggests something important. The universe that produced quantum entanglement also produced, through the same physical laws operating at greater complexity, the experience of being connected to other minds. The universe that is, at its quantum level, a single entangled whole, has also produced at the level of conscious beings the experience of reaching across the separation and touching something real. The quantum world and the human world are not separate. They are the same world seen at different scales. And the themes that appear at the quantum scale, connection, correlation, the refusal to be cleanly separated, reappear, transformed but recognizable, at the scale of human experience. This is what physics at its deepest gives you, not just equations and predictions and technology, though it gives you all of those. It gives you a picture of a universe that is, at every scale, coherent, connected. One thing, seen from many perspectives, always following the same rules, always generating the same deep patterns of relationship and correlation. Entanglement is one of those patterns, perhaps the deepest one. Two particles, correlated across any distance. The universe, one entangled whole. You, here, now, part of it. That is enough. More than enough. Actually, one more thought. About John Bell specifically, because his story deserves more than a footnote. Bell worked at CERN as an accelerator physicist. His job, day to day, was to calculate how to keep the particle beams in CERN's accelerators on track. It was important, skilled, demanding work, but it was not where his heart was. His heart was in the foundations of quantum mechanics, in the question that everyone else in physics had agreed to ignore. In the 1950s and 1960s, there was a strong consensus in physics that foundational questions about quantum mechanics were not real physics. They were philosophy, or worse, metaphysics. The Copenhagen interpretation had provided a working framework. The theory made predictions. The predictions were confirmed. What more could you want? Asking what quantum mechanics meant, what the wave function was, whether collapse was real. These were questions that serious physicists simply did not spend time on. Bell disagreed. He thought these were real questions with real answers. He read Einstein's arguments carefully. He read Bohm's pilot wave theory. He thought about what it would mean for there to be hidden variables. And he realized something that had escaped everyone else, that you could test the hidden variable hypothesis, that you could design an experiment whose results would distinguish between a world with hidden variables and the world that quantum mechanics describes. He derived his inequality in the evenings and weekends, in the margins of his real work. He published it in a journal that was, at the time, somewhat obscure, and for years, almost nobody paid attention. It was not until John Clauser, a young graduate student who also cared deeply about the foundations of quantum mechanics, read Bell's paper and decided to actually do the experiment, that the community started to take notice. Clauser had to fight to get permission to do the experiment at all. His advisors were skeptical that it was real physics, but he persisted. He built the apparatus, he ran the experiment, and the result was what Bell had predicted. Bell's inequality was violated. Local hidden variables were ruled out. Even then, it took years for the broader physics community to recognize the significance of what had been done. It was only when Alain Aspect's more refined experiments in the early 1980s attracted wide attention, and only as quantum information theory began to develop, and physicists realized that entanglement was a practical resource, not just a philosophical puzzle, that Bell's theorem came to be recognized as the landmark result it was. Bell himself never sought celebrity. He was modest, precise, and slightly uncomfortable with the attention his theorem eventually attracted. He gave lectures and wrote papers, but he was always more interested in the physics than in being famous for it. He just wanted to know whether Einstein was right. He found out that Einstein was not. And in doing so, he produced one of the most important results in the history of science. He died too soon to see it fully recognized. But the physics is permanent. The inequality is there. The experiments have been done. The universe has answered Bell's question. And the answer is, Einstein was wrong. The universe is stranger than common sense allows. Reality does not pre-exist measurement in the way we assumed. Distant particles are correlated in ways that no local realistic theory can explain. And the universe, at its deepest level, is not a collection of separate, local things, but a single, entangled whole. That is what John Bell, working in the evenings and weekends at CERN, discovered. That is what a generation of experimenters confirmed. That is what quantum information theorists are now building technologies from. And that is what you now know. Two particles, entangled. The universe, connected. You, here, part of it. Before I let you go, one last thing, and I mean it this time. The reason entanglement matters to you, right now, tonight, is not because it will change how your coffee tastes or how your car runs. It matters because it changes what you can honestly say about the world. And what you can honestly say about the world is the foundation of everything. If local realism is false, and the experiments say it is, then the mental model most people carry around, the picture of a world made of separate objects, each minding its own business in its own location, is not an accurate picture of the deepest level of reality. It is a useful approximation, valid at the scales of everyday life, but not the truth. The truth is stranger. Objects are not fully separate. Properties do not fully pre-exist measurement. The universe is not a collection of independent things, but a single, interconnected quantum state in which separation is approximate and correlation is fundamental. This does not mean that everything is magically connected in a vague New Age sense. The entanglement between distant particles is real and measurable, but cannot be used to send information or influence events at a distance in any controllable way. The non-locality is physical, not supernatural. It obeys precise mathematical rules. It is constrained by the no signaling theorem. It is quantifiable and experimentally testable. But it is real. And knowing that it is real changes something in the way you see the universe. It means that beneath the appearance of separation and independence, there is a deeper structure of connection and correlation. It means that the universe is, at bottom, less like a collection of billiard balls and more like a vast, vibrating web of quantum relationships, in which what we call objects are regions of particularly intense correlation in that web. That is the universe entanglement reveals. A universe of relationships rather than objects, of connections rather than separations, of correlations that span any distance and cannot be explained by anything traveling between the correlated things. Einstein called it spooky. Bell showed it was testable. Clauser and Aspect and Zeilinger confirmed it was real. And now it is yours to carry forward, to think about, to wonder at. Good night. And thank you for staying with it all the way to the end. The universe is strange. It is stranger than it needs to be, stranger than any simple picture of reality can capture, stranger than the intuitions built up over millions of years of human evolution were designed to handle. And yet it is precisely, beautifully describable by mathematics, testable by experiment, knowable, at least in part, by minds like yours. That combination, deep strangeness and deep knowability, is one of the most remarkable things about the universe we find ourselves in. And entanglement is one of the clearest windows into that combination. Strange enough to have unsettled Einstein, known well enough to be used in quantum computers and cryptographic systems, understood just enough to reveal how much we still do not understand. The journey is not over. It has barely begun. Physics has been asking the question of what reality is made of for thousands of years. It has found atoms, and then particles inside atoms, and then fields underlying those particles, and now entanglement woven through all of it. Each answer has revealed a deeper layer. Each deeper layer has been stranger than the one before it, and there is no reason to think we are at the bottom. Entanglement may not be the last word. It may be one step on a longer journey toward a picture of reality that is stranger still, and more beautiful still, and more true. The physicists working today on quantum gravity, on the emergence of space-time from quantum information, on the black hole information paradox, on the foundations of quantum mechanics, they are pulling on the threads that entanglement has revealed. And what those threads lead to, nobody yet knows. But we know they lead somewhere. The universe has surprises left, and the minds capable of finding them are, right now, doing the work. Perhaps one of them is listening tonight. Good night.